All right. Hello, welcome back. So far, we have been talking about describing the motion or describing the causes of motion, the Newton's second law. But as before, if you remember how we started talking about positions, velocities, and acceleration, we started talking generic without a real way to calculate these. And later, we saw how we can write those kinematic variables in different frames. Similarly, these generic equation of motion, sum of forces equals mass times acceleration, they are rather generic, and depending on the structure of the problem, we may want to use or select a certain frame to write these vectoral kinetic equations in. So note that when you have sum of forces equals mass times acceleration, we have different choices. We can either write these equations in rectangular frame. We can write the same equations, but in a tangential normal frame or in polar frame. And today in this class, in this video, we will see rectangular frame. In the next two videos, some details about tangential normal and polar frame. And I'll finish this section by talking about system of particles. But for now, let's see what we mean by writing these equations in a rectangular frame. Rectangular frame, you have your nice and familiar XYZ frame. And remember that for these equations to work, accelerations must be expressed in an inertial frame. So let's assume this frame is fixed, it's not moving. And you have a particle, a force. No, let's not use that direction. I don't know. Some force like this. This is the net force, or let's assume for now it's just one force. What you can do is write this F in three components. So it has Fz, Fx, and Fy component. It's the same vector. I'm just writing it. Let's make Fz a bit taller. I made a mess. Okay. And you can write this vectoral equation of motion. Let's go with just one F for now, equals mass times acceleration. You can break it into the three components of the rectangular axis. Write Fx equals mass times acceleration along x. Fy equals m-ay. Fz equals m-az. So this is probably the most convenient, easiest frame, because you can separate the kinematics along the separate axis. You can do the same thing with the forces, separate the forces along the three directions, and work with individual, now scalar version of the same equations. And probably this is what you have been doing all along in the physics classes. One other thing, if you have more than one force, you can continue and doing the same thing. Let me make it a little nicer. Find the total component of forces along the x, along the y, and along the z axis, and then continue writing the equations the same way. For instance, a good use case for this situation is, again, projectile motion, because the force the only force acting on the system is gravity. It is always in the same direction. You can write the three equation. Sum of forces along x is 0. From here you can get ax equals 0. Sum of forces around y is, well, let's x, y. Let's call this one z in this case. Ay. So ay is 0. Sum of forces along z is minus mg equals mass sum acceleration in z direction. So acceleration in z is minus g. This works well for this frame, and this framework works well for projectile motion. So that is the first frame. Let's look at two other frames, see how we can do equations of motion in those frames. So I'll see you in the next videos.